Hey guys, we were using the harmonic series today, and we found out that it does diverge. But we did it with the calculator, and I kind of showed just a very brief explanation. But I didn't really get into it too deep. I didn't think I really had the time. And one person had asked in period 7 for clarification, and I kind of rushed through it just because I knew I wouldn't really be able to do it justice. So I promised to give a better explanation, and I don't have my document camera with me, so I had to make a PowerPoint, but I can still record it. So hopefully this will help explain why the harmonic series does actually diverge, and this way you just have to take my word for it. You'll actually get to see it for sure. So here we go. Here's your harmonic series, 1 over n from 1 to infinity, and I listed a bunch of terms. And the idea here is we do know that it passes our little gateway test, right? So the idea is even though the limit as n goes to infinity of my sequence is 0, that doesn't necessarily guarantee convergence. In fact, in this case, this series actually diverges. So let's see why that happens. It seems like it should converge, but for some reason it doesn't. Let's look. All right. Let's list out the first set of partial sums. I think this is what we did in class. So the first term is just 1. The second term, the second sum would be 1 plus a half, then 1 plus a half plus a third, 1 plus a half plus a third plus a fourth, etc., etc. Focus your eyes in on the second sum and the fourth sum, actually. The second sum first is equal to nothing fancy, just 1 plus a half. I just want to set that as like the foundation, because my fourth sum is actually going to be greater than 1 plus a half plus a quarter plus a quarter. So if you notice, I did a little bit of shenanigans here. I changed the 1/3 to a quarter because I want to show that my original sum is actually bigger than this sum. And this sum is equal to 1 plus 2 halves. Yes, I know that's a 1, and 1 plus 1 is 2. But I want to show there's going to be a pattern brewing here, and in order for me to really show that, you have to see it this way. So again, my partial sum for 4 terms is 1 plus a half plus a third plus a fourth, and that has to be greater than 1 plus a half plus a fourth plus a fourth, because 1/3, of course, is greater than 1/4, and that's the only switch I made. So that means this fourth sum is greater than 1 plus 2 over 2. Okay? My second sum is 1 plus 1 over 2. My fourth sum is greater than 1 plus 2 over 2. Well, I'm not going to stop there. This isn't really a pattern yet, so let's go again. Let's go to the 8th one. Okay, my second sum is still there. My fourth sum is bigger than the 1 plus 2 over 2. Now my 8th sum. So 1 plus a half plus the 1/3 and 1/4. I did the same shenanigans that I did up here, and then I did even more shenanigans. I turned all of these into 1/8. If I turn all of these into 1/8, well, clearly this partial sum is going to be bigger than this partial sum. 1/5 is bigger than an eighth. 1/6 is bigger than an eighth. 1/7 is bigger than an eighth. 1/8 obviously is the same, but nevertheless, I've accumulated way more. Well, maybe not way more, but I've accumulated more for sure in this sum than I did in this sum. And the blue sum simplifies to 1 plus 3 halves. 1 plus a half plus another half plus another half is 3 halves. 1 plus 3 halves. So 1 plus 1 half, 1 plus 2 halves, 1 plus 3 halves. You know we got to do one more. How about 16 terms? All the way to 16. Okay? I'm going to do shenanigans. My 1 half is here. This is the same shenanigans as my sum 4. This is the same shenanigans as my sum 8. And now what I did was I changed all of these 9, 10, 11, 12, 13, 14, 15, 16 to 16ths. And clearly, this partial sum is bigger than this partial sum. And if I simplify the blue partial sum, I'll get 1 plus 4 halves. 1 plus 1 half plus 2 halves plus 3 halves plus 4 halves. Let's summarize. My second sum was, actually that should be equals to, sorry, not greater than, 1 plus 1 over 2. My fourth sum is bigger than 1 plus 2 over 2, 1 plus 3 over 2, 1 plus 4 over 2. So let's generate a formula for that. If I use powers of 2, because that's what I've got here, 2, 4, 8, 16, 2 to the n would represent the partial sum that I'm focusing on. And it's either greater than or equal to. Again, the first one it happens to be equal to. So my partial sum is greater than or equal to 1 plus n over 2. So if n is, say, 1, right? So s of 2 to the first would be here, is greater than or equal to 1 plus 1 over 2. 1 plus 1 over 2. Okay? If n is 2, that would be S sub 4. That would be my fourth sum, is greater than 1 plus 2 over 2. If n is 3, 1 plus 3 over 2. If n is 4, 1 plus 4 over 2. So this is my formula to represent my partial sums being greater than or equal to this, particular pattern. Well, this is not stopping at 16, obviously. It keeps going. I could do 32. I could do 64. I have to go to infinity. So let's take the limit as n goes to infinity of our partial sum, which is greater than or equal to the limit as n goes to infinity of our pattern. But our pattern as n goes to infinity is 1 plus infinity over 2. That's not bound. That's infinity. So this series diverges because my limit as n goes to infinity is infinity. It does not converge to a particular value. Okay? So it's a little tricky, I know, and if I had a little more time in class today, I probably would have been able to go through it, but hopefully this will help at least for you to buy the fact that the harmonic series does have to diverge, guaranteed, and I promise on Friday I will actually show you another reason why this diverges. But for right now, these are the only techniques we know, and this is the way to show it. Okay? Let me know if you have any questions. I will talk to you guys later.